systems of equations was, but pretty easy. So section 7.4 is where we're going to start logarithms. All right, so the key to doing logarithms is a fancy word for it acts like an exponent. So that's the thing that you've got to keep in mind as we're going through this stuff, especially today and then tomorrow as we solve equations, is that a logarithm is an exponent. An exponent. That's the kind of the idea you want to keep kind of rolling in the back of your mind, is that logarithms act like exponents. And their uses are to take really, really, really small numbers and make them kind of regular, or take really, really, really large numbers like national debt size numbers, trillions and trillions of dollars, and make them manageable, more normal numbers. That's what they're really, the uses for those are. But a log has a base, and this is kind of how the thing goes here, is that you have log of some base, and we'll talk about, that varies from problem to problem, and then of something. So the log base 5 of some other number is equal to the exponent. What we can do here is rewrite logarithms as exponential ideas and rewrite exponentials as logs. So we're going to start by getting the property of rewriting a log as an exponential. And an exponential, what that means is it's a statement that has exponents in it, okay, instead of logarithms. Okay, so this is like the first property of logarithms that we'll use. So log base 2, and the base is always written like a subscript there. Log base 2 of 8 equals 3. If we're going to rewrite that as an exponential, you remember when you write exponents, exponentials or powers have a base. It's the same base as the log. So the base is the base of the log. The exponent is what the log is equal to. And then it's equal to whatever you're taking the log of. So 2, that's that 2. 3, that's that 3. And 8, that's that 8. That's where those numbers are coming from. Rewriting a logarithm as an exponential. It really, that's all we're doing here. We're not doing any work to get there. Tomorrow we'll do some equations, and if you can rewrite the log as an exponential, sometimes the equation's a lot easier to solve. Instead of doing things with logs, you can do things with exponents, and it makes it a little easier to solve. Log base 3 of 81 is 4. So if we're going to rewrite that as an exponential, what's the base? 3. The exponent is equal to, notice that that's a true statement as well. 3 to the 4th power is 81. That's true. It's mathematically correct. They're going to be that way if they're numbers. If there are letters in there, it doesn't change things very much. And if you throw a log base 5 of x is equal to y, something silly like that. It's got x's and y's in it. Algebraic, I guess would be the way to say that. If we're going to rewrite it as an exponential, we're really not doing anything else to it. We're just rewriting this as an exponential. It's going to be 5 to what power? Y equals x. Real simple idea is rewriting those things as exponentials. Okay. Now, where they can throw you a little bit with this is when they do this, log, and then they don't write a base there. And they'll just do something like 1,000. What base do we think this could be? Close, really, really close. What to the third power would give me 1,000? 10 is the only number to the third power that would give me 1,000. So if they don't put a base there, you got to understand that that's a log base 10. The reason a 10 is one of the natural logarithms that we or common logs is what it's called, is because we live in a base 10 number system, that we have a ones digit, a tens digit, a hundreds, thousands, 10,000s, all base 10 system. So a common log, the log without anything written there, is going to be a log base 10. Okay, so anytime you see that with nothing there, it's a log base 10. Another common log is ln, or natural log. We'll do 148.413 equal to 5. Now, this one is a little bit different. It's the natural log, used a lot in biology and the natural sciences. Thus the natural log idea. The number that it's the base with, it's really log base E. And if you remember from biology, like bacterial growth or cell reproduction, it's an exponential growth curve that happens with that. It's log base E, and E is just a number. If it's E to the first power, it's about 2.71 is about what it is. So, but it represents, I got a whole bunch more desks. It never ends, actually. It's kind of like pi, is what E is kind of like. It comes up enough that they gave it its own symbol. They chose the letter E for that number. If we're going to rewrite that as an exponential, it would be E to the fifth is equal to 148.413. But what you've got to tie together is that natural log is really log base E. That's going to be very helpful when we go to solve some equations, log base E or natural log. In order to undo it, you have to use an E involved. And in order to undo a log base 10, you need a 10. In order to undo a log base 5, you got to have a 5. The base that the log is key to being able to solve equations that have logs in them. So that's an important thing. All right, so rewriting the logarithm as an exponential is what all that is about. Let's go the other direction. Let's take a exponential and write the exponential as a log. So when we look at these exponentials, we're going to look to see what base it has and then use that for our log base. What letter are we on here? F. So if we had 5 to the third power is 125. That's a true mathematical statement. If we're going to rewrite that as a logarithm, what base log do we have? 5. Log base 5. That's that 5 right there. Of 125 is equal to the exponent 3. A logarithm is an exponent. So the log should be equal to whatever the exponent is, because a logarithm is an exponent. Is in math is equal, right? So this logarithm is equal to the exponent. And sometimes I've had students in the past that say, oh, it's easier if you just put the equal sign and put the exponent there, and then that just eliminates one of the numbers, so you only got to get the other two right. Say we had like 6 squared is equal to 36. You know that's true. What I'm saying is that, a lot of students, they go, oh, well, it's equal to 2 because that's the exponent. So I know that's where it goes. And then what log base? 6 in this case, because that's what the 2 was on. And then of 36. We've written an exponential as a log. 5 to the x is equal to 30. Log base 5 of 30 equals x. Right. Good job. You could put x equals log base 5 of 30. You could, yeah, it doesn't matter what side you do that on. 10 to the 5th power. 100,000. How do we rewrite that? Log basic. It really is base 10, but we don't usually write that of 100,000 equal to 5. Yes. Yes. Yes, ma'am. All right. So we got E here. So what log is it? Natural log. LN, because it's E is the base. What's the exponent on that E? If nothing is written there, it's a 1. So we know it's equal to 1. So it's the natural log of 0.71 is equal to 1. All right, let's look at evaluating some without a calculator first. I'll show you how that's it directly relates to this. So it's an application of this is what it is. And then I'll show you with the calculator. All right. Log base 4 of 16 is what we want to evaluate. The way that I do this, and it kind of leads us toward the solving of equations stuff later on, is they give me this as the problem. They don't have it equal to anything. We've got to find out what it simplifies to be. The way that I do it is I just put it equal to x and then rewrite it as an exponential. Because if I'm evaluating this without a calculator, it should work out to be a nice number. Shouldn't be a decimal as an answer. Okay. So if I rewrite that as an exponential, what does it become? 4 to the x equals 16. And then we just think, okay, well, 16 is really what? It's really 4 squared. And if 4 to the x is equal to 4 squared, what does x have to be? It's got to be 2. So that means that log base 4 of 16 simplifies to be 2. Won't always be that direct, but it is that same idea. Let's go to one that's a little bit more difficult. Log base 2 of 32. Some of you may have the base 2s memorized. I don't know. Always one in the crowd. This is what I normally do if I've got to evaluate this and I'm told to do it without a calculator, which remember on your EOC, there's a portion without a calculator. And I always expect them to put these on there. 2 to the x equals 32. If I don't know my 2 exponentials, I just think, okay, can I break down 32? Like factor tree style, elementary school stuff on it. So it's 8 and 4. That's 4 and 2, 2, 2. So 32 is really 2 to the what? 2, 3, 4, 5. 5? Yeah. 2 to the 5th. And if 2 to the x is equal to 2 to the 5th, what does x have to be? Be 5, right? So log base 2 of 32 is equal to 5. That's what we're kind of doing here. It really doesn't much tougher than this. Let's do one more without a calculator, then we'll do one with a calculator. I'll show you how to find log base 3 of 27, and let's evaluate that. So I just put it equal to x. Say 3 to the x is equal to 27, and then I think, what's 27? 27 is really 9 and 3. It's really 3 to the 3rd power. So x has got to be 3. So log base 3 of 27 is equal to 3. Evaluating it without a calculator. When you're evaluating without a calculator, it should work out to be nice numbers. That shouldn't be any kind of crazy stuff going on there. All right, let's look at with the calculator. Let me get my calculator open. I'll show you how to do different log bases with your graphing calculator or any calculator that's got a log button on it. All right, so evaluate with a calculator. All right, a couple of different ways to do it. One way involves using the log base function on your calculator, which is easy to do. Let's get an example. Log base 2 of 12. We know 2 to a power, a nice one, doesn't get 12. If it was log base 2 of 8, that's an easy one to do without a calculator. Log base 2 of 16, log base 2, 32, 64, 128, 256. All those numbers are easy with 2s. 12 is not, because 12 has 3 in it. So that's not even a base of a 2. So to do that with the calculators, a couple of different ways. I'm going to show you. The first way is with the log base function, which you get by hitting the math button. And then the up arrow. And you see that log base there? Hit enter. You should get something looking like that if you've got a TI-84. If you're using an 83, the solid black one that doesn't have any other color, you can't do it this way. Okay. Put in the base 2. Press the right arrow. Put in what you're taking the log base 2 of. And hit enter. 3.585. Let's go 3 decimal places with this stuff. Now, if you, for some reason, don't have your graphic calculator, but you've got a regular scientific calculator that has a log button on it, okay, you can use what's called the change of base. All right, so the way the change of base form works is you can use the regular log button right here, and you can do log of 12, close the parentheses, divided by log of whatever base it is. If it's log base 2, you'd put the base goes in the bottom. That's the way you want to remember that. And it gets you the exact same number. Okay, so if your graphing calculator dies, you don't have one handy, a regular scientific, I think these have a log button on them somewhere. Easier to see if somebody didn't color all over this one. Yeah, there it is, right under the second button. So most scientifics have a log button on them that can be used for such as this. Okay. Really helpful when you get into problems that have fractions as the base. Log base 1/3 of 28. And we're going to get an approximation for that. So if I'm using the graphing calculator, I can use that log base, and then that'll put a 1/3, and then a 28, and crank that out. Negative 3.033. If I don't have that, I can still do that log using the change of base formula. Log of the big number divided by log of the base. Oops. Yeah. Same answer. That's called the change of base formula when you do it with two logs there. Log of 16. What log base is that? 10. You've got a log base 10 button on your calculator. It's that one right there. It says log. That's log base 10. So we don't have to do the log base. You could go ahead and do that and put manually type the 10 in there, but you don't have to if it's log base 10. 1.204. Same way with natural log. You've got a natural log button on your calculator. Approximation symbols look horrible today. The LN button is just below the regular log button. Natural log of 6. 1.792. Okay. There's not a base written there. If there's nothing written there, it's understood to be a 10. The natural log is always log base E. Is the way that works. That's what that LN stands for. Log base E is, I guess, shorthand for that. Not that it's much shorter, but that's the symbol that it generally gets. Okay. Of course, everybody wants like 14 of these or 4 of these on the quiz because that's easy. It's nothing to it. But anyway, we don't use that a whole lot. All right, let's look at the next section. Section 7.5, the properties of logs. So the first property that we talked about was the changing it from exponential into logarithmic and from logarithmic into exponential. These properties are a little bit more creative, I guess would be the right way to say it. We'll just do properties of logs. All right. We have what's called the power property. And you'll need to memorize these properties so that you can use them. Log base B of M to the n power. So I'm putting variables here. The generic thing, we'll do some examples with these in just a little bit. We got a base here of something with an exponent on it. So it's a power property. What the power property does is it allows you to take this exponent off of that and bring it down to the front. So that's n times log base B of M. Okay. Multiplication is easier to get rid of than exponents are because you don't have to do a root or something. You can just do division and get rid of that number now. So that makes solving the idea of the properties is that so that you can solve equations much easier with simpler methods. So the power property takes an exponent from inside of the log out to the front. That's what the power property says. The product property. What's a product in math? What kind of operation gets you a product? Multiplication. And remember we said that logarithms are really what? They act like what? Exponents. When you multiplied things that had the same base, what did you do with the exponents? Like x squared times x to the fourth. When I do x squared times x to the fourth, what do I do with the exponents? I add the exponents. So what happens here with the product property is that you've got a log of some base of two things multiplied together. The product property says, oh, it's a logarithm with things multiplied together on the inside. You can break that apart into two smaller pieces that are added together. Okay, the product property takes the multiplication of things and makes it addition, and inversely does the opposite there. If it's addition of two logs that are the same, you can turn it into a multiplication and condense it down to one log, which is very useful in solving equations. Get the quotient property. What's quotient in math? Division. And when you divide x to the fourth divided by x squared, what do you do with the exponents? You subtract them. So the log property, if you have two things divided inside of a log, then you can turn that into a subtraction problem. All right. So division turns into subtraction, multiplication turns into addition, and then exponents turn into multiplication. That's what we got to remember about these properties. Okay, so the first thing that we're going to do is expand the logs. And we're going to expand those using these properties that we've talked about here. Okay, example A, log base 3. These properties work no matter what log base we're using. Okay, I'm just randomly picking log bases. It really doesn't matter what log base we use. We could use log base turkey if we wanted to. It really doesn't matter. Okay. So we have the log base 3 of x to the 7th power. So we have an exponent inside of a log. So the power property says that we can take this 7 and do what with it? Move it to the front and make it multiplication. That's right. We've expanded that log. We've taken it from the log of something into something times that log. Now, so about as easy as they get right there. It's going to be a little bit more difficult as we go here. Log base 2 of 3x. We're going to expand that. So we need, if we're asked to expand a logarithm, we need to think what operations are going on the inside. What operations going on the inside here? Multiplication, which turns into addition. So we have log base 2 of 3 plus log base 2 of x. And we've expanded that log. Real simple so far. Keep it simple. And then we'll step it up a little bit on the next one. What's going on inside of this log? Division. So it turns into subtraction. So it's log of x minus log of y. Order matters. on the division. Okay, top minus bottom. Okay, always in that order. I usually, even on the multiplication, just still keep it in order until I need to move something when I go to solve equations. Okay, so there's an example. What log base is that? 10. Okay, good. Make sure we catch that, because that just sneaks in there every now and then. All right, let's complicate it and put more than one property together. Okay, so it's log base 6 of 5x to the third over y. So yeah, let's just dive in. Like diving in the pool for the first time in the spring. What operations are going on inside of this log? Got an exponent, got division. Also have multiplication, because I got that 5 times that x to the third. Okay, so we've got all three, got three things going on here. So it's easiest sometimes to do it one piece at a time, or just get some stuff taken apart. So the biggest thing I see there is the division. Anytime we see the fraction kind of idea, we usually want to get rid of that. So if I split it apart with that, this is what it would look like. But now, this guy doesn't have anything else going on, right? But this one has a lot going on. So what can this one do? Before I can do that, I got to undo the multiplication, because the x is the only part that has the exponent. The 5 doesn't. So I need to split that apart to log base 6 of 5 plus log base 6 of x to the third. And then I've still got the minus log base 6 of y. And then that 3 can come to the front, but only for that piece. The risk that you take in moving it first is that you forget, oh, that 3 doesn't go with the 5. It only goes with the x. So here we have log base 6 of 5 plus 3 log base 6 of x minus log base 6 of y. And that's completely expanded because nothing else can be done. Now, as you're doing these, some of you can probably do it right now. You can do more than one step at once, and you wouldn't need to do 3 different lines for that. Some of you could probably go straight to this blue line without doing anything else, and I'm fine with that. Okay, but if you're ever confused, do it one step at a time. That's always the best policy, is just do it one step at a time, and you can get there. All right. Let's do another one of those. Let's do log base 2 of 4 to the x, or 4x over y to the 5th. What letter am I on here? E. So we got division going on. We've got what else going on? There's some multiplication there in the numerator and an exponent in the denominator. Can we go straight to the answer here? Let's see if we can. I think we can. We're smart. What does that numerator turn into? That's the denominator. The numerator. There you go. And then for the 5 log base 2 of y, it's a minus, yeah. Yeah, there we go. And that's expanded there. So we're splitting apart the division. The things after the minus sign are division. and then the numerator was multiplication, so we made it addition. All right, let's throw a chain in the spokes here. Natural log 10 x to the fourth times the cube root of y. Learn a little something here. What's going on between all of those? Too much? Maybe. But what operation? Between the 10, the x to the fourth, and the cube root of y. It's all multiplication. So we know it all is going to turn into addition, right? So we know that it's going to come out to be natural log of 10 plus, what about the x to the fourth? Can we do something with the 4 exponent? Well, the power property says that 4 exponent can come to the front. And then here's something that you may not know. The cube root of y is actually y to the 1/3 power. Those are the same thing. Okay. The way that works is whatever the index of the root is the denominator for the fraction power. So if it's a cube root, it's 1/3. If it's a square root, it's 1/2. If it's a fourth root, it's 1/4. If it's a fifth, if this is a 5 right here, it's 1/5. It's a really easy idea. But that knowing that is what's happening allows me to then go, oh, it's 1/3 natural log of y. And now we've expanded that. Probably not a lot, no. An equal amount, I guess. Mixed in with all this other stuff we got going on. Quite a bit of stuff in these two sections. I think I'm going to like this, doing it this way better. In the last couple of years, I've been putting the properties and the solving in the same day. And I think having the properties a day ahead of the solving may help with the solving, because you got to have the properties to be able to solve. So, all right, so we've expanded. Let's condense. And when condense something, you make it smaller. So you think about the condensed soup. You know, ever eat chicken noodle soup, condensed soup? It's condensed. You got to add water to it. So we're condensing down a big problem into one. Okay. You might see this. The instructions say write as a single log. That's another way of saying that. I learned it condense, and I've never changed from that. That's the way I've always said it. So condense. All right. So we're going to give you one that's expanded already. Log base 2 of x plus log base 2 of y plus 5 log base 2 of w. All right. So condensing this, you got to look at the operations that are happening. You've got addition, multiplication out in front by a number, and think, okay, so addition turns into multiplication. This 5 out in the front really came from where? An exponent on the w. So it's just undoing everything that we just did. So this should be log base 2 of x times y times w to the 5th. Now, obviously, when you start using this to solve equations, it's not going to have 3 variables in there. It'll have 1, but the idea is to be able to condense it together and build one log, and then all we got to get rid of when we do the equations is get rid of 1 log instead of 3 of them, which is much easier to do. All right. Let's try a tougher one. Log base 7 of 3 plus 2 log base 7 of x minus log base 7 of 5 minus 3 log base 7 of y. Ooh, 2 operations in there. And really 3 operations because you got multiplication too. So we got addition and subtraction in there. So that makes, if there's subtraction in the problem, that makes me think what? Division. Makes me think, okay, there's a top and a bottom. What things would go on the bottom? Yeah, the 5, the things that have the minus sign, it would be the things that go in the denominator. All right. And then the things that don't have a minus sign in front of them are the numerator. Okay, so these 2 things together would be log base 7 of 3x squared. Good job. Now, the denominator, both of those are minus, but does this make some sense? That this is really another way of writing that. Factor out the minus sign and they're added together on the inside of those parentheses. So that actually becomes what? 5y cubed. Good job. And it all goes where? On the bottom. 5y cubed. You condense that, pretty tough problem, into 1 log. Anytime you see minus signs, you got to know that stuff's going to go in the denominator. Anytime you see plus signs, oh, that means they're multiplying together, usually going to be in the numerator. All right. Natural log 4 plus 5 natural log x minus parentheses natural log of y plus 4 natural log w. This one similar to the previous one, but just one little major difference. What we got? We know it. Okay, multiplication and division. What's the numerator then? 4x to the 5th power. Good job. The denominator. YW to the 4th. I'm going to write it W to the 4th Y because alphabetical order in my brain matters. It doesn't really matter mathematically. That it's also correct to do YW to the 4th, but minus sign out in front of the parentheses again throws all of that after that minus sign into the denominator. Be careful of that. Sometimes they put those parentheses in there. Sometimes they don't. And you've got to pay close attention to it. This one, log base 8, or log of 8, not log base 8, log of 8, and then 2/3 log of y minus 6 log of x plus 3 log z. We want to condense that down. Z, 3 log of z. Another variable there. All right, so we know it's going to be log of something. We see a minus sign in there, so we know there's some division going on. What's in the denominator, the bottom part of the fraction? What part has the minus sign? All right, so the x gets what power? 6. Does this part have a minus sign? No. Is there parentheses around both of those parts? No. So that last part, even though it's after that minus sign, it has a plus sign on it. So this is one of the trick things that they do. They kind of try to throw this in there and say, okay, well, there's a minus sign on this, and you kind of automatically think, well, everything after it should be in the denominator. But this is not negative. So it should be in the numerator. So we know z to the third should be up there. What else should be up there with it? I'm going to show you another way that could be written. So when you're checking answers, you may see it a different way. That could be 8 the cube root, or 8z to the third. That's how they would write it. The cube root of y squared over x to the sixth. Both of those are correct. That's the way that I would probably write it. And way I would expect you to write it on the quiz. But if you're checking answers like in the book or on a practice activity that I've got for you, they may write it with the root involved. Again, the denominator is the index of the root, and then since it was squared, it's squared on the inside. That really is about as tough as they get, guys, on condensing. They don't get any tougher than that one. That is as hard as they get. The kicker is just looking for those pluses and minuses and making sure you know when everything after the minus goes in the denominator or if it's not everything. That's the real kicker to this. Not really much more on the complicated side than that. All right.